I'll be demonstrating Coulomb's law using the Coulomb balance. There's a torsional balance, meaning that we are twisting a fine steel wire that is attached to this adjustable holder here and to this dial here that I can turn like so, and turn one end of the wire, which generates a very small torque on the rotating part of the apparatus here, which is a coated, carbon-coated ping pong ball basically on an insulating rod there. And then we have a piece of aluminum sheet metal that's shaped like a cut piece of pie. And in this inset image here, you can see in this close-up that we have a set of marks on our balance here, one on the frame and one on the pie-shaped piece of aluminum that forms one half of our arm here, our torsional balance arm. And when I line those up, I need to make sure those are lined up whenever the spheres are touching, and I have 3.8 centimeters on our track there to the left, where our stationary sphere is located. I've adjusted that so that the distance, it is accurately reading this distance of separation between the centers of the spheres. I also made sure that when there's no outside force on the sphere, the dial will be reading 0 and the marks will be lined up. And so that is all the alignment procedure. Now I'll go ahead and start the experiment. I've adjusted my power supply to 6 kilovolts here, and with our spheres separated, I'll go ahead and touch one and touch the other, and then very quickly I'll move these in to 20 centimeters. I'm getting about 18 degrees of dial rotation to get the marks aligned. And then I'll go ahead and discharge them and repeat. That was for 20 centimeters. We ended up with 18 degrees of dial angle. And now I'll go ahead and with our spheres separated, I'll repeat this. For 14 centimeters. And I'm getting about at about 40 degrees. 40 degrees of angle to bring my torsion balance sphere back into alignment here. 40 degrees. I'm having to hurry here because the whole time I'm working to adjust and get this aligned back in line here, I'm losing charge. There's charge constantly bleeding off of these spheres because our insulation is not perfect. And so I have to work very quickly because my voltage the whole time I'm doing this is decreasing from the known 6 kilovolts that I start with. and we don't have a good way of tracking that, so I'm just having to hurry as best I can. And so that is the challenge of this experiment, is to get it as lined as best you can, as fast as you possibly can. Discharge these, separate them again, and now we'll move down to, from 14 centimeters down to 10 centimeters. And I think I'm getting about 78 degrees of angle there at 10 centimeter separation. Next we'll move down to 9. And I'm going to get about, looks like I'm coming in about 96 degrees. Yeah, we're coming in about 96 degrees at 9 centimeter separation. And we'll move down to 8. And it looks like we got about 120, maybe 122 degrees. It looks more like 120 degrees. 120 degrees at 8 centimeters. Next we'll move down to 7. And I'm seeing 153 degrees at 7 centimeters separation. And we'll do 6 centimeters next here. And I'm seeing about, 195 degrees at 6 centimeters separation. Yeah, 195 degrees at 6 centimeter separation here. And finally at 5 centimeter separation, I'm seeing about 245. It's 245 degrees of angle on the dial at 5 centimeters separation. And at these ranges, we're going to start to have some significant uneven distribution of charge. So treating these as point charges at this point is a little bit far from reality, but that's the best we can do with the limitations we have with this apparatus. So that concludes all of the data points we're going to be taking here.